Welcome to electricity. You are transitioning from the macroscopic world of moving masses to the microscopic world of moving charges. This unit is the absolute foundation for all electrical physics. It is a story of energy transfer, what carries it, what pushes it, and what opposes it. You simply cannot analyze a complex multi-loop circuit until you deeply understand the behavior of a single component. In this unit, we define the fundamental vocabulary of electricity: charge, current, voltage, resistance, and power. We will build a chain of logic step by step.
We begin with the charge carriers themselves. Current is simply the rate of flow of charge. But to truly understand it, we must look inside the wire. The drift velocity equation links the macroscopic current you measure to the microscopic world you cannot see. It depends on the number density of charge carriers, the cross-sectional area, the mean drift velocity, and the elementary charge.
Once you have charge carriers, something must push them. This is where examiners set their traps. You must master the precise difference between electromotive force and potential difference. Both are measured in volts, but E.M.F is the energy supplied to the charges to drive them, while PD is the energy the charges deposit into components. Remember, voltage does not flow.
Next, we examine what opposes this flow. You will calculate resistance, but more importantly, you will explore resistivity. This property depends on the material itself and its physical dimensions. A classic Paper 1 question will ask you to calculate the new resistance if a wire is stretched. To succeed here, you will need to think in ratios and handle unit conversions perfectly. How does current respond when you change the voltage? You will sketch and explain the IV characteristics for metallic resistors, semiconductor diodes, and filament lamps. A major trap is assuming that the resistance is the gradient of these curves. It is not. Resistance is strictly the ratio of voltage to current at any specific coordinate. You will learn to explain these shapes using physical principles. Finally, we tie it all together with electrical power. At what rate is electrical energy converted into useful work or dissipated as heat? You will learn to seamlessly switch between 3 different power equations depending on the circuit context. You will also evaluate practical energy usage, calculating the total energy transferred in joules and evaluating commercial energy usage in kilowatt hours. By the end of this unit, you will have a complete toolkit for circuit analysis. You will be able to track the flow of charge, calculate the energy transferred per coulomb, determine the resistance of any wire, interpret IV graphs, and calculate electrical power. This is the essential vocabulary of electricity. Let us get started.